This is week 10 of Stochastic Control and Communication. I'm Purva and I'll be taking this tutorial session. Let's get started. Okay. So I'm facing a little bit of internet issue. So I'll go through the notes from uh, I'll go through the notes that were used in the class itself if mine doesn't show on the screen. Okay. Yeah, it vanished again. Right, so for the time being, this is what I'm going to do. Okay, so uh, today we're going to talk about the Witsenhausen's counterexample and a few variations of that to understand where that example is coming from and what it means. In the last session, we had talked about the same thing but very informally. First, we started out by understanding what were the two types of information structure, meaning the classical one that we have seen already and the non classical one. And we went through a few examples of that. After we went through some examples, we looked at a real world example of what um, any normal system with a controller and a sensor device together can be thought of as a multi optimization problem and thought of as multiple controllers instead of just one. So, in that, we saw that the previous assumption was if we are encountering an LQG problem or a LQ problem with some independent noise, then we expected the controller part and the estimation part to be independent of each other, and we could solve for those in different ways. And both of them don't need to be solved together. But Witsenhausen's example, the counter example says that's not the case. What is believed to be linear strategies, which seem to be optimal in case of normal LQG games with classical information structure, that no longer holds if the information structure is not classical. And to show that, he constructed an example. So this was his example. So in this example, x0 is the initial state, then that is an observation that is available to the controller at that point. So the first controller looks at the information and chooses an action or makes a policy, and we're denoting the policy as gamma 1 of y0. Then using that, the next state is created, and that state is x0 plus u1. Now, this state is not visible to the next controller. Some noise gets added, and that after the noise is added, that particular is the observation of the next controller. So, what is happening here is controller first controller and second controller don't know the same things. That's point number one. Point number two, for controller 2 to infer what was known to controller 1 and use that information to try and optimize any further, it needs to know a little bit more. Either the noise shouldn't be present or it should know something else from the problem itself. That tells us that this is not a standard classical information structure. This is a non classical information structure. And here the actions u1 and u2 are coming from some policy gamma 1 and gamma 2. Okay, I think now my give me just 1 second. I think my iPad will connect now. Okay. Yeah, this is better. So today we're going to try and understand what is this counter example in more detail. So we do remember the basic setup of the problem itself. We had x0, x1 and x2. We had some observations y0 and y1. And our task was to optimize this cost. Optimize this cost in with respect to some gamma 1 and gamma 2. And gamma 1 and gamma 2 are, so u1 is gamma 1 of the information available at that point, so y0, which we know is just x0 itself. On the other hand, u2, the action of the second controller, is coming from some policy gamma 2, which depends on gamma 1, and gamma 1 depends on x1 and this noise v term. And we know x1 itself has dependence on u1, so this is gamma 2 of, and u1 is coming from the function, so it's a complicated uh, dependence, but this is the dependence. Okay, and with this kind of a dependence, we're supposed to minimize the following cost. The minimization is with respect to gamma 1 and gamma 2, and we're minimizing this guy, k square u1 square. Let's write that in terms of gamma itself, gamma 1 of x0 whole square, and the second term is x2, and x2 is x1 minus this, so that is x0 plus gamma 1 of x0 minus the action u2, and u2 is this one, u2 is gamma 2 of take a square of that, and that's what we're trying to optimize in this problem. Now recall, this is the part that we had discussed last time, and this is the part that we're going to talk about in more detail and be more clear and specific about it from this point onwards. The action of, or the rather the policy of controller 1 affects two things here. One, it affects the cost, clearly it affects the cost in a direct manner, and on top of that, this gamma 1 is affecting the policy gamma 2 also. Gamma 2, along with some other things, is a function of gamma 1. So this dual dependence becomes a little bit complicated to handle. It suggests that linear may not be the only kind of solutions possible. Linear strategies or linear actions or linear policies may not be the only solution possible. And that's the idea that this work, Witsenhausen's counterexample, is trying to get at. Okay, now recall, in MDPs, there was some dependence. When we wrote out the MDPs, so the past actions did matter, or for controller 2, the actions taken by controller 1 still mattered. It's not like that was completely ignored, but there it was an action, so a step taken and the state was observed, so we knew what state we were in, and hence we were able to make the next steps. But here, this is a partial information type of a situation. We do not know, so for controller 2, he does not know what is the state. Some noise got added. He doesn't know x1 itself. If it knew x1, then this problem would have been a bit different. So, as a comparison, in MDPs, okay, where did that go? Yeah, as a comparison, in MDPs, past action still influences the current actions. It not only affects the current actions, it's also going to affect the cost. That part is fine. This, what does this term mean? We'll come to that in some time. In the condition that we are talking about here in Witsenhausen's scenario, it's the policy that matters. It's the past policy that has influence here, not just the action. current policy. Here, if you recall, to solve for gamma 2, all that needs to be done is we are just solving a mean square error problem if we want to solve for gamma 2 or find the optimal gamma 2 star. So gamma 2 star, just one second. Gamma 2 star in this type of a problem, let's say it's with respect to some variable t, is just making an estimate of this, and this is x1. So making an estimate of x1 given what it knows about x1 plus the noise, the observation y1. And since we have taken t here, this means this random variable ends up being equal to some realization t. And we could write it out more explicitly. We could write it out in the same form as here, and that would give us gamma 2 star has a clear dependence on gamma 1. At this point it's just gamma 1, it's not even gamma 1 star. So, and we know if we are talking about the case where these things, the initial state and the initial state and the noise are Gaussian, then this would end up just being something uh, linear. So it would end up being linear in this t, and it would be something like some constant times t if mu and this were Gaussian. Right? Now, if we were to use the same logic, but in case of an MDP, in MDP what would happen is, oh, this is not MDP. Suppose we take the case where x0 is known. So this part is as it is. Along with this, x0 is also known. So knowing x0 and this component, which we know has some dependence on gamma 1. Now what is happening here is, because we know x0, if we had gamma 1 as just a black box, we could plug in that x0 in the gamma 1, reconstruct this much, right? And if we have managed to reconstruct this much and we know this whole thing, meaning we have managed to reconstruct the v also. In other words, this is just the same as saying that this information is the same as this information. One can be reconstructed from the other. So when we say reconstructed from the other, meaning there is some sort of a black box assumed which allows us to know what gamma 1 of x0 would be. In that sense, now this has become slightly more easier to handle, and this is the scenario when the second agent, the second controller, knew the information that was known to the first controller. So now this is actually y1 and y0, and now this is a classical information structure type of a situation. If you want to understand this slightly more carefully, so assume we have some function g of t, which is the estimation of f of x given f of x plus some v, where we are saying that this whole thing is some random variable whose distribution depends on x, the noise or whatever this v is, and the function f, versus the scenario if suppose we knew this x itself. So if we knew this x, it is possible to use this x and along with that, suppose we have the noise also. If we have these two things, then it's possible to reconstruct this, given f is like a black box available to us, in which if we pass through this x, we'd get whatever construction we want. So this scenario has more information versus this one, or in other words, this is the standard non this is the non-classical information structure, this is the classical information structure. Okay, so the point of this is the difference between standard MDP type problems, or problems where there is classical information structure, versus the situation where there is a non-classical information structure. Okay, then let's talk about what would happen if it was in MDP. In an MDP, first of all, notice we won't be making an action, we won't be choosing an action like this. There won't be an estimation problem. It would just be that action u1 will be based on whatever is known at that point of time. So let's say that is y1, or to be more specific, y1 is x0 and y2 is so this one is just u1 would be some function of x0, and this would be some function of x0, this will be some function of x1. Now another thing that happens when we are talking about a non-classical information structure, which is something that doesn't happen in problems with classical information structure, is that these controllers, the actions of these controllers are affecting two things. One, they are affecting the action, they are affecting the cost. That part is obvious. They have some effect on the cost. But they may have influence on each other also, as we just saw for the Witsenhausen's example. So it's gamma 1, gamma 2 would be affecting the cost, of course, and gamma 1 would be influencing gamma 2 also. Because of this kind of an influence, now if we only focus on gamma 1 has dual purpose, and this type of a dual effect is something that we're going to focus on in today's tutorial. So this scenario where you see
this thing,
yeah,
g of x versus another g of x. Yeah, here, if you know the x, f of x relevance is not present. Like you can't ignore in a condition case. So is it a kind of signaling, or its signaling is different?
sorry, which one are you talking about, this case or this case?
Second one where we, because if knowing small x, making the irrelevance of f of x, if you know the properties of f. Okay, but since f of x is a random variable, it's valid on expectation side. But
No, f of x is not a random variable, no.
then
F of
expectation.
x, whenever I'm saying it's the whole thing which is a random variable, mostly because this part is the random variable. This part is the random variable, but f as a function is a deterministic function. Or it may be a probabilistic function also, as in we could have a probabilistic policy. That part is fine. But
Oh,
this on its own won't be f on its own won't be uh, a random variable.
okay.
It's function on a
You,
random variable, so the whole thing is sure, but what that function is already, let's say, predefined.
okay. You remember that the stochastic control and MDP equivalence, there was
Mm-hmm.
a scenario where we had a noise plus some state, and we put state condition on something, and we make the probability is equal to noise
Hmm.
is equal to something. So here, if f of x is somehow known, this will go to only v, right? And v, if you know, then everything is known.
That's what is happening here, no? That's exactly what we're saying. So in the scenario where along with this one, this is y1, right, and this, let's say, is same as y0. So if you knew both of these things, this is the same as saying you don't need to care about what is f of x plus v. You basically have the same information as having v and x, and from here you can construct this part, or from here you can construct this part.
Correct. I'm questioning that expectation, which expectation will drop, something like that, because v is known.
It depends.
Depends. Okay.
So f of x may still have a dependence on v and x.
Okay.
It depends on what kind of a v and x you have. If they are Gaussian, then this will all just become something linear.
Yes.
Linear in the vector vx now. But in general, we're not saying whether it is a Gaussian or not. It's just some random noise, and x may be some initial variable. So this was just a repeat of what I said above.
Mhm. Yes.
This was to
Okay.
illustrate it slightly more cleanly. That's about it.
Okay.
Yeah. Okay. So where were we? Yeah, we were talking about what is called as the dual effect. So dual effect is if basically if the information of controller u1 influences the policy, I should have written controller 1 influences the policy gamma 2, but this information itself is not known. If that is the case, then apart from influencing the cost, it is now having effect on the policy also. So having two effects is why we're calling a policy as having dual effect plus
The
affecting cost.
impact on other policy completely makes sense, but for the cost, if K1 is zero, that I can avoid.
So we're taking the general case. Obviously you can take k10 and hence it will not affect, but in general your policy, you're choosing a policy to optimize the cost, right? You're choosing your actions to optimize the cost.
So
So
basically, design of cost is important.
yeah, see, this part is a general fact. This is not new. Policy affects the cost because that's what it is trying to minimize or optimize. This part is what is not common. That the information of some controller is affecting the policy of the other controller. This is policy of the other controller, but that information is not available to the other controller.
Oh, sorry, I did mistake. See, if K1 is zero, still it will impact the cost because X2,
Huh?
my
Yeah,
mistake.
yeah, it will.
Yes. Yeah.
Exactly how it comes up inside is a different point, but it does. Okay, so now we're going to talk about what is dual effect a bit more carefully. And once we have talked about dual effect in a few variants, then we'll finally go to how Witsenhausen actually handled the counterexample. How did he make his arguments? At least to an extent, we'll go through that part. So now, um, okay, so this is just like a FYI. Again, I'm not gonna go through this part in much more detail. Um, when someone talks about information structure, they're actually referring to things that come from sigma algebra and measure theory and so on. But while we are using those type of terminology and language, for most purposes, it suffices to think of them in almost layman terms and just work with it. If you wanted to go with the truly formal and proper approach, then it requires going through sigma algebra, proper probabilistic approach, using measure theory and all of that. So here, now this is the new symbol that is coming up, where this sigma is the sigma from the sigma algebra, and this basically says that Z is something that is produced using the information of W. That's what this reads as. So this is what we'll use in writing out the Witsenhausen's counterexample and then see a few variants. So these are the initial states, action of controller 1, the information of controller 1. Now we know u1 is something that depends only on the information x0 it has, meaning we can write it according to the standard way of writing information structure. So u1 would be something that is produced from the information of x0, so we're writing it as u1 belongs to sigma of x0, and similarly u2 belongs to sigma of y1. Okay, so it just means that u1 and u2 are coming from the knowledge of x0 and y1 respectively, and this is the same stuff. So we're ultimately minimizing over u1 and u2, and we're looking for the particular the way the knowledge is derived from x0 and y1 such that this gets minimized to the best possible way. Okay, so now let's look at the following scenario. Uh, Recall that we have actually talked about some of these scenarios in the last week's tutorial and the lectures also. There, the focus was on understanding whether something is classical information structure or non classical. Right now, what our focus is to understand if whatever information structure we have, does it have dual effect? And the variants will actually show that there might be dual effect, but it may not matter enough. So I'll come to those things. So let's say we're talking about this kind of a information structure. So this information structure for u1 nothing has changed, it's still the same thing. For u2 now, u2 is constructed using the knowledge of x0 and the noise. Remember in our variation, the not the variation, the original version itself, x0 x0 oh, x0 plus u1 gives you x1, and with that we're adding noise. So if we know u1, if we know x0 and we are able to actually get all of this information. So in that sense it's full observation, and but the observation is actually of the noise, so we know the exact the realized value of the noise at any given point of time, and that is being used by controller to choose its action or policy. So now let's focus on this one a bit more carefully. So this can be written as if u1 is known and added to both of them, it's still the same as before. Or even more, even better, we could say this is the same as having x1, which is the actual observation, so it's x0 plus u1. So the only difference between this information and this information is here u1 is also being used, but it's there in both of those terms. And this one is the same as sigma of x1 and x1 plus b. And same arguments as before, we can use these two and construct this variation. Notice to the whole purpose of all of this is we need the observations, the actual sorry, not the observations, we need the actual state to make the best decision possible, or to make the best action possible. So with that idea in mind, if we know the noise and we know the initial state and we know how to get to the next state, then we can always create that. And hence these two information structures, this and this, are actually equivalent. We can go from here to here. And if that is something that is allowed, which means x2 has the the controller 2 has the information about x1 and this noisy observation, both of these are available to him. He can use that knowledge of x1 itself and make u2 equal to that. So he can just make this term completely zero if he knows x1, and which is the case, he knows x1. If that happens, he managed to get a linear policy at this point. If that is the case, that is okay, sorry, that is one situation that can happen if u1 itself was 0. And there's nothing. So if controller 1 had not taken any action whatsoever, then this was possible. So here, the way I have talked about it, we still needed to know what u1 was. So if u1 was taken to be a constant, then these two are by default exactly the same things, and you don't even need to know u1, which ended up being a constant no matter the value of x0. And because of that, now we know all of these things. We know x1, action u2 is taken according to that. And since this is 0, these two are taken to be equal, this whole thing becomes 0. And hence the cost is the minimum possible cost, since everything is real. We're taking squares and everything is real, so the least it will do is half. Sorry, 0. So the point here is, in this particular variant, is there a dual effect or not?
Yes, it is.
How?
Because if you see the u1 is, if it is not 0, if u1 is not 0, when you add them, okay,
In
I
general,
think
yes. In general,
no,
sure.
I
But
think no, no, it is not there.
If I'm only talking about the optimal case, because that's the one that will matter the most, right? If u1 is made a constant, it doesn't matter if I'm just adding that constant, which is anyway 0. Then these two information structures have become the same, and this information structure,
Okay,
or
means there is no
this
dual.
information structure knows more than this. It has this information plus something else. Same thing here.
It is same as classical information by the way.
Yeah, this is proper classical information type of scenario, and hence there is there is no dual effect in this. If there was dual effect, that would have showed up
But I had one
either here or
basis
here.
question on this.
Hmm.
Like why are we focusing so much on dual impact, dual effect thing? Like, is it that much important? Like, what's the
Dual
relevance?
effect makes it very difficult to solve certain problems. For example, Witsenhausen's.
Mm-hmm. Because the whole week sir have spent only on this
Yeah,
week.
he has
So
spent the whole
I,
week talking about dual effect.
yeah, I was surprised. Like, what's the importance of this?
It tells us that dual effect may be there in certain problems and it may not matter. For example, it's there in MDPs also, but there it doesn't matter because, well, it doesn't affect it so much. So yeah, because the true observations in an MDP situation with Markov policy, the true states are known. We can just use that. We don't have to depend on some observations. And since we are using the true state, that information is enough to take the current action. We can use DP algorithm and so on. But in scenarios where dual effect is present, meaning there is interdependence of actions or policies to be more specific, and one policy affects the policy of someone else's who doesn't even have the same information as the first guy, then this interdependence makes it difficult, and it breaks the whole idea of being able to use DP type algorithms. That is the core problem. That's why Witsenhausen's problem still can't be solved to get an optimal.
Okay, so basically the edge of Bellman equation, like we can't apply directly.
Hmm. We can't apply the same logic that we had in Bellman. Yeah, Bellman equation was fine. We used a DP algorithm after that, right? We used
Yes,
what
yes.
what was the other name of it?
The principle of optimality.
Principle of optimality was used, right? That can no longer be used. We were able to use it at that point because there were no observations. That was first thing. There was no interdependence this complex that it played an effect. Here, it's playing an effect in two ways. It's not only affecting the information that is available to any particular control about the information of the previous one. That part is definitely there, but it has effect on the cost also because it shows up in an implicit manner in the cost. Like here, where is Witzenhausen's? Yeah. Even though we're minimizing over gamma 1 and gamma 2, this term is okay. But here there's a gamma 2 and inside of that there is a gamma 1. So this non-linear dependence tells us we can't really use DP at this point. At least not in the standard ways. There may be other ways of doing it which I'm not aware about, but so far it seems that DP can't be used here.
Okay.
So the reason for spending so much time, I believe, is because this is a very important class of problems. Things that happen here actually are natural, that happen in team type scenarios where there are more than one agents, maybe acting sequentially or maybe acting simultaneously. Now games can have both of these effects. So in team decision type problems, this becomes even more important. Okay. So yeah, you can stop me and ask me doubts because I felt this week's Videos, if you just go through them once, they were okay. uh, but there may be points in between that were maybe not clear, so you can ask them. Otherwise, today's plan is that I'll go through whatever was covered in the lectures itself.
Yeah,
It's like a recap
definitely.
of at this point.
Only the last part when the Witsenhausen proved this, that part I may have question. This part is okay.
Okay, so I'll just go over this with some speed in general, assuming there may be other people who might watch at a different time. And then once we come to that, you can ask whatever doubt you have, okay? So, where were we? Right, so first variant is if there is full noise observation. In that scenario, these two information structures are equivalent, or these two informations are equivalent. Now, variant 2 is this one, or in other words, now what is known as y0 and y1. Y0 we know is x0, and y1 is x0 plus u1 plus v. And since we know u1 is something that depends on x0 and that x0 is already known, meaning we can use this x0 to reconstruct this much portion, whatever the way may be to reconstruct it, but we can, knowing what is needed. And once this reconstruction is done and we have all of this, meaning we actually know what this noise is. Point being, these two, ah, this and this are equivalent. So the variant where what is known is different but something can be inferred, in that sense they're equivalent. So here what is known is observation y0 and y1 is what is known, and that is being used to find the action u2. But the way these two are, the way they're constructed, is such that it's the same as knowing it, it's enough to just know x0 and v. And same as before, if this is the one we are following, here the policy of one is no longer important. It can be some constant policy or something, as we saw in the example above. So the idea is, again, there's no dual effect in this problem as well, and dual effect is basically referring to the scenario where the information of controller 2 or u2 depends on the policy gamma 1, the policy taken by the previous controller. Now let's take another variation. In this variation, what is happening is, let's say u1 is something that is produced knowing y0 or knowing x0. That's scenario 1. And in the second scenario, u2, for u2 we know u1, meaning we know the action taken by the previous controller, and we have our observation, but we don't know the true state. So even though we know u1, here we can't really deconstruct this part. Knowing u1, we can remove this, but we're still left with x0 in the noise. Notice this is different from the previous scenario. In the previous scenario, because we knew y0 and y1, where u2 knew this much, so we were able to easily reconstruct. And u1 is anyway something that depends on the information x0. So this is just related to x0, so we already can figure this out. This is the only remaining thing, and hence that's why this reduced to sigma x0 and v. On the other hand, here What is known, sorry, is the observation y1 and the action taken by the other guy. Now, using that action, we still need to infer what must have been the information available to him. If we can't make that inference completely, it's still not complete information. Something is still missing. And that's exactly what is happening. Even though we know this u1, we can't remove this v altogether from here. In that sense, this and these two are different from each other. And the claim for this particular problem was that this has dual effect. Meaning, whatever is the choice, whatever is the choice of gamma here affects what happens to gamma 2 here. Or it affects the information and that affects the gamma 2. So now there are two situations where he does this kind of a proof. And the idea for these proofs is we don't need to look for all the scenarios where we see this dependence. If we are just claiming that there is dependence, if we show it once, meaning if it's there in one scenario, it's there. That's all we need to worry about. And that's all we're going to show through just two extreme examples. And the ideas of those two examples is very similar. First, we are taking the case when gamma 1 is a one-to-one function and it can be inverted. Both of these things mean if I know x0, sorry, I should have said it the other way around. If I know u1, I can invert this gamma 1 to get x0. So what happens because of this? Notice this u1 is a function of gamma 1 x0. Here also it's the same thing, but here it's directly. Now if I can reconstruct and find what x0 is, since gamma 1 is invertible, that means this information is the same as having the information x0. And now since I know x0 and I know this whole thing, it's the same as just knowing v itself. So this is just talking about what can be reconstructed from the other. This is case 1. So this is one type of policy we're considering, and we're talking about what is it equivalent to. Now let's take the other scenario where gamma 1 is a constant, some constant c. If that happens, then here there's some constant, but knowing this constant, I know nothing about what x can be, meaning I'm still stuck with x0 plus mu. So it's still something that depends on the sum of these two quantities, and hence this can't be in general equal to the point that is to be noted over here is the choice of gamma 1, whether it's 1 to 1, invertible, or a constant, affected the kind of information that is available to the second guy. And if the information of the second guy is affected by the policy of first guy, then the policy of second guy would also be affected by that. And hence, in that sense, this variant has dual effect. Is that okay?
Yeah.
Alright. So now, another thing to point out here is this particular variant. In this particular variant, we can't even find an optimal solution. notice what is happening in this variant is this is the new this is the new component. Apart from the observation, we know the action taken by the previous controller. So u1 is okay. U1 is something that depends on the observation. So let's say things are linear. Let's take a simpler example. Let's say there's some epsilon and we want to keep our cost less than this epsilon itself. It's some epsilon greater than 0. So let's say u1 has the following form, and u2, since it can depend on u1, the dependence just comes as u1 divided by gamma divided by epsilon. So it becomes the same as x0. We could write out the cost in this case and we would see this cost is something that depends on epsilon square and the expectation of x square, or the variance of x square. This is x0. Now this means we can take this epsilon to as small value as we want, and if we do that, we could minimize the cost. We could take the cost even to 0, and if we manage to take the cost to 0, that means we do have a meaningful u1, but the problem is we don't have a meaningful u2. Meaning, even though optimal cost should be 0, but there is no policy that can achieve that. And since there is no policy that can achieve what is the optimal cost here, that's why I was saying in this particular variant there is no optimal solution. So knowing the action of the other guy, you can make some inference, but that inference will not be enough to come up with a way to get optimal cost. In general, that's the case. Now the next now once again, before we get to the next variant, notice what is clashing over here in this example. If we want to get the cost to be 0, we need u1 to be 0, because there's a straightforward term with k square u square. As long as there's some u1 square value, that term will exist. So we need to first tune that value to 0. If we tune that value to 0, then that means u2 just becomes equal to x0. But u2 is a policy that needs to be found out using this information, u1 and x0 plus v. Since u1 is 0, this is anyways not useful, so all that is remaining is this component. But now this component, there is some noise, and we don't know what that noise is. We don't have information about that noise. So finding the actual x0 from here is not possible. We can estimate it, but we can't actually find it. Meaning our estimation is always going to be off by some amount, and that amount by which it is off is exactly the term that comes up here. I wrote it wrong. This is the actual one, and this, if it is an estimation, it's the difference of that. The estimation error is what we are trying to minimize. And if we are doing an estimation, on an average, there will be some error remaining. It will not go to 0 by default in every situation. Meaning, even though there is an optimal cost which is believed to be 0, it doesn't seem achievable in this scenario.
If it is Gaussian, then we can have an unbiased estimator, right? Then we can estimate without error. Hello?
No, I'm just wondering. So, if you had Gaussian, but see, okay. So let's say what you're saying is you have x0 as Gaussian and v as some Gaussian,
Yes.
right? If you have addition of
Let's
two
see.
Gaussians, let's say they're both with mean 0. So the mean won't get affected, but the variance will get affected. Variance of the joint is no longer the same as the original one.
Mm-hmm.
That will have an effect on your estimation,
Okay.
right? You'll not get the exact x0. There'll be some error. Either that's some alpha error or some additional error, but it'll be different from the exact x0 value. That's the meaning of estimation. Estimation means you get to the best possible estimate of something, which means you can't actually always get the correct value. You might hit the correct value once in a while. So it's in that sense that we're saying that getting an estimate which is correct all the time is not possible. Or finding a U2, sorry, gamma 2, where the information is this, exactly equal x0 is not possible. So this combination is the one that is likely to suffer because of this problem. So we could try to have some u1 value. So let there be some u1 and have that u1 somehow share some information to eliminate the effect of noise. If that kind of a thing happens, then good. But if there is some u1, the cost will have the presence of that term, so it will not go to 0, which is the trade off or the idea that's being highlighted here. Okay, so now,
Yeah.
so far I've talked about three variants. The first variant is full noise observation. Second variant is just what is observed is different, or what is known to the controller is different, but it ends up being the same as the previous scenario where uh, x0 and the noise was known. Okay, let me point it out this way. For example, here, if you know x0, you don't need an estimate of it, and you can make your y2 to be equal to x0. But if you don't even know x0, you can't do that. You'll be making an estimate, and that estimate will be off by some amount in general. No matter how good the estimate is, it's still an estimate, right? Alright, now let's come to the fourth variant. This isn't exactly a variant, this is the standard stuff. This is to point out that if there is a dual effect doesn't mean there is always a problem. If that dual effect affects the cost in some implicit manner also, then there is a problem. And that's what this variant is going to highlight. So this is the standard situation where we have a normal MDP. We know the actual states. There are no observations needed. The observations are perfect otherwise. And the policy is Markov. So this is with Markov policy. With Markov policy, this means that u1 will be chosen based on the state. Let's say the state is x0, and u2 would be chosen based on the state x1. If this is the scenario, then the claim is that there is still dual effect in this problem. So now let's try and see this part. We'll do the exact same thing as the previous variant. We'll construct two different gamma 1s and see do they lead to similar kinds of u2. Our point to prove this claim is as long as there is even one, sorry, as long as there is only one pair of gamma 1 which leads to situations with dependence and without dependence of gamma 2 on gamma 1, then it makes the point that there is dual effect, and that's all that we need to do. So right, let's take the same situation as the previous one. So now gamma 1 is such that it's invertible, meaning from gamma 1 you know x0. So that part is there. Now gamma 2 is something that depends on x0 plus u1, and u1 is something that depends on it depends on some gamma 1, right? And now we know this. From here we can reconstruct, and we know x0 is out here, meaning this is the same as having that x0. Wait, did I? Okay, just give me 1 second. I need to rethink this one. Okay, in the meantime, let's look at the second scenario where gamma 2 is such that, sorry, gamma 1 is such that it's some constant minus x. Then u2 would be sigma of x1, and x1 is x0 plus u1, which means actually this is just gamma of c, and that's just a constant, so there's no information. So see what happened. In this scenario, I think this is correct. In this scenario, because we can reconstruct and get gamma 1, we can get x0 from the whole of this. We know the exact form, we know that it can be constructed from here. So knowing this, we can get a way to make this whole thing invertible and get x0 itself. So in the first scenario, we have x0, let's say, meaning the information is actually present. The information of the first one ends up being present in the information of the second one. But in this scenario, there's no information whatsoever. Because of the difference or the effect of gamma 1 in the two scenarios, this tells us that gamma 1 does affect the policy of the second guy. And if that is the case, then that means there is dual information. Yeah, is this where you had a doubt, or is it still further on?
Yes, exactly this point.
Okay, which point?
Uh, this this statement, like if gamma 1 is chosen like c minus x, leads to uh, like sigma of c when there is no information.
There's no information of x0 or x1 or anything of that sort. There is information from C, but it doesn't matter to us.
Correct, correct. And uh, but like we know that POMDP we have the y0 and y1, but this is only for like I don't know, like little confusion on this step.
Okay. Let's recap a little, huh? This is standard Markovian policy, meaning there is no y0, y1 here, whatever. We were calling it y0, y1. So there's no such thing as y0, y1 here.
Okay, so do
Or,
we know that controller 2 knows u1?
okay, so right, I think this is not written clearly. So what is happening here is y1 is x1, y0 is x0, meaning perfect observations are made. If we put it that way, then it's the same structure, right? Then x1 must be the same as before, x2 must be u, what is it?
X1 minus
Right,
u2
x1 minus
u2.
u2, right? So that same thing is being used here. This is what is being used. So this is what is written here. And now what we're saying is u1 is something that depends on a gamma 1, and this whole thing, we're assuming that this whole thing is invertible. That's how gamma 1 is. If that is the case, then from here we can tell what is x0. So this information, so u1 actually depends on the information x0. That's scenario number 1. On the other hand, in this scenario, that's not what is the case.
Okay, so through this we are telling a different gamma, we have different values like previous cases.
So see, we started out with some gamma 1, gamma, we started out with some gamma 1 here, and some gamma 1 dash, and whatever is the effect. All we are comparing is, does the information that is available to controller 2 get affected by changing gamma 1? Just changing this, does it affect the information available to the other one? That's what we are trying to see. If that happens, then that is what is defined as dual effect.
Okay, finally.
Yeah.
Yeah.
So now in this situation, the difference is here what is being used is x0, and here, well, there's no information of x0 whatsoever, so u2 might end up just being a constant or something. Now if we were to go by such a scenario, we were to consider the fact that since this is a problem with dual information, how do we solve for this? Notice, for u2 it knows x1, right? u2 is constructed using the information of x1, meaning we can always make this 0 by taking u2 equal to this. So this got sorted like right away, and then we can take u1 equal to 0. So the whole cost is made 0 by taking this, and we were able to do this particular step because u2 is something that is chosen using the information of x1. The point is, at times it might be possible to, depending on what kind of gamma was chosen, it might be possible that u2 has information about x0 also, because it can be reconstructed from knowing x1. But nevertheless, that's not even needed for this optimization problem, because this is all that needs to be solved.
So in short, we have a dual effect, but cost we achieve it minimum cost.
Exactly. So the reason why Witsenhausen's problem is difficult is because there is dual effect, and that dual effect has its bearing in the form of the cost also. Remember, this is something we saw last time. If we change the cost so that maybe one term is not there, it is possible to optimize it even in non-classical information structure, and I think we actually get a linear actions or linear policies in those situations. The
Yes,
problem is both of these things together can be too complicated to handle.
yeah.
Oh, is my screen not visible? Okay. Okay, just give me 1 second. Um, Now we'll go to. So we've covered the variants. Now we'll finally go to Witsenhausen itself. I am just trying to reconnect my iPad. It got disconnected again. Okay. Till the time it's not getting connected, I'll use the lecture notes. Okay. So now we're finally going to talk about the Witsenhausen's problem itself. Okay, started. Right. So this is the standard Witsenhausen's problem. The way he did it in his paper itself is he reformulated the problem. He, instead of looking at x plus x1 of x plus gamma 1 of x and some gamma 2 of x, he rather focused on some f and g functions. So ultimately the cost becomes k square x minus f of x whole square. Fine. And x2 is x1 this part is gamma 2 of f of x0 plus and a whole square of this. And here it is also x0. Or I could write, instead of gamma 2, I could just replace it by g. And remember, g is still, to get g, we're just supposed to optimize this. This is a mean square problem, mean square error problem. And the solution to this is the estimation, which is that we are trying to estimate x1 using whatever we know at this point. And whatever this is, and we're taking this to be equal to some t. Whatever this is, whatever that best response is to a given f This is going to be something that depends on the choice of f itself, right? Because this expectation is something of this sort. So it's x0. Let me just write it as x1.
So in the expectation x0 plus b, why it is there?
Sorry?
In expectation x0 plus noise,
We're supposed to take expectation of x1, right? We're estimating this given this information.
then it is x1 plus v, right?
Is it x1 plus v?
Because
No, no.
x0,
We are
the
estimating x1 given x1 plus v.
x1 given x1 plus v.
That's
Okay.
the real thing, right?
Yes, yes.
Have I written this term correctly? Is this correct? Uh, so put x as x0. That becomes this becomes x1, right? This fx0 is actually x1.
Yeah, I'm feeling that only, like x0 is x1 here.
Oh,
But
okay. You're saying instead of this, I could have just written it as x1 is just fx of 0. Right.
yeah,
Yeah,
kind of.
correct. Okay, this is better.
And this has exactly same form which we were discussing.
Yeah. Just the point to note over here is the choice of f will matter. The choice of f will dictate what will be g star of t. So that's why it's good to have f in the subscript to remember that the choice matters. The choice of the previous controller's policy matters here. Okay, so this is the reformulation that was done. Now let's try to go further. Now, before we directly go to the solution or the solution that is given by Witsenhausen himself, let's understand it a little carefully. And for that, what we're going to do is we're going to take first the scenario when f is linear and see what is the best response or what is g star. In the opposite scenario, we'll take g to be linear and then see what can we say about f star. So what is the best response of f star knowing g is linear? Typically what would have happened is, so it's like fixing one but finding the optimal for the other, and then fixing the other and finding the optimal for this one. This is similar to what is called as person by person optimality, especially in team games type of a situation, and that's what this would come out to be. But the point is, it's only in very specific scenarios where this person by person optimality ends up being equal to team optimality, meaning when we were optimizing both of them together, not one at a time, and which is why linear to linear is the one that's not going to work. So anyway, let's come to that. So we're starting by saying, let's say f is linear. So f is not even x. Let's say it's some gamma of x. Then Remember, this is still a mean square problem. If it's a mean square problem, what we're ultimately trying to do is estimate this, and this estimation is basically getting an estimate for lambda x0, knowing lambda x0 plus this noise, and let's say this is equal to some t. Now if we assume x0 and v are both Gaussian, which is what is actually talked about in Witsenhausen's counterexample also, he focuses on LQG problem. So if that is the case, then this is something that's just linear in t. Okay, so recall what we were trying to do here. We started by saying, okay, let's assume f is linear. With that assumption, the best response for g star is a linear policy. It's something that's linear in the variable t here, or the parameter t. It's not a variable anymore. Let's reverse it and ask the question, what if we did the opposite? If g itself was made linear in t. So recall, this was expectation of some k square. At this point I don't know what is f, so I'll have to write it as it is. Here it is. Is that correct? So here we know g itself is linear, so we could rewrite this. Let me copy some of these terms.
Can we use the logic right if G is linear, which means the joint expectation is a Gaussian function? Can we use that logic?
We're not worrying when it is linear. Gaussian is one possibility. Joint Gaussian is one possibility. It may be linear for some other reason also.
Okay.
And okay, at this point, to be more specific, I am not saying g is the best estimate. G is just some function.
Mm-hmm. Okay.
So I am not saying it is the best one already. I have not fixed. So here in the process of fixing one and finding the optimal for other, I am not saying that I've fixed the other one to the optimal. I've just fixed it to something. Because our argument is mostly about linear functions, that's why I fixed it to linear.
Okay.
Yeah. So now here what happens is, yeah. Now you can write this more carefully, and it's just completing the squares and all of that. So this is fx0 minus 2 fx, okay. So this is 1 minus mu fx0 and square of this. We could plug all of these together by completing the squares. So that would be from here this kx0 and some other terms. In the process of completing the squares, the other terms that you'll get will be the ones without this fx of 0. You could ensure that happens by simplifying it a little bit and converting this to, not going to do that process, say that there is some a you've taken outside. Some other terms again. Now, since the other terms don't have x0 in them, if you do it properly, okay, if we're doing it properly, we'll not get a k here, it might be something else. Okay, let me call it k dash, something else, doesn't matter what that is. This is now again the standard estimation problem. This is just mean square error that we're trying to minimize. And if that is the case, right. So fx0 would be the estimation of this k dash x0 mu v given whatever is known at this point. So what is known? y1 is okay. What is known at this point?
Do we know the x? Wait, this is generally we put y there, and what is y in this formation? It's minus y whole square.
And that's what okay, I got disconnected again.
Technically should be f of x.
Or it might just be x itself, or x0 to be more specific. One second, where did it go? Can you see the screen I'm presenting?
No.
Let me try rejoining then. Yeah, I think it's just whatever is known, right? Typically that's how we go about it. So it's estimating something based on knowing x0. Remember, this f of x is actually gamma 1, and at that stage what is known as x0. So the estimation is supposed to be based on that. That makes sense. Which means this quantity should be something that's linear in x0, some function. So maybe some, okay, let me call it lambda. Your screen is not visible. 1 second, I'm still trying. Right. So, right. So, remember, this fx0 is actually related to gamma 1. That's how we defined it here. And at the stage of gamma 1, what is known is just y0 or x0 itself. So, this estimation is based on x0, meaning this should be something that is linear in x0. So, or you could say x0 has a certain value, whatever you want to call it, x, and that's what this will be linear in. But nevertheless, it's a linear function. So the point to note over here is, we started out by, we did two scenarios. We took f to be linear, then we got the best response to that for g was to be linear also. In the other scenario, what we did is we took g to be linear, and we saw that the best response for that also, in that scenario, the best response for f is to be linear again. Meaning, this is similar to the idea of so here what I'm doing is, if I'm keeping one fixed, so if I'm taking this linear, it just so happens that this will be greater than okay, so this is the second scenario that we just talked about. The other scenario, the previous scenario, is if we took f to be linear by choice and then try to find what should be optimal g, then we found that this is this is going to be always greater than jfl g star. It so happens that g star also becomes linear. This is true for all g, this is true for all different types of, what are we wearing? We're wearing f. And now look at it and try and recall if this looks familiar. So, in game theory, yeah, if you recall something, go on.
Yes, yes, this is kind of a Nash equilibrium kind.
It is kind of like that. So, what it seems like is, unilateral deviations won't help them. They're supposed to deviate to the best one together. But here, what is happening is, we are fixing one and finding, or we're fixing the type of function for one and then finding what should be the other. Same scenario is repeated here also. This is not the same as saying, okay, before I go further, let me write it slightly more carefully. This is situation 1, this is situation 2. This is the one that we've actually talked about so far. Situation 2 would have been, for all f and g. There are possibilities where one holds, but that does not imply two. And there are also similarities when one holds, it implies two. The first one, In team theory language, it's called person by person optimality, where we're fixing the policy or the strategy or the action of one and then varying the others and repeating that for all the other agents or all the other controllers. This, on the other hand, is both or all the controllers and all of them are trying to do it together. They're trying to optimize at the same time. So, in general, these two may not be the same. And that's exactly what happens in this Witsenhausen scenario, also. So, what we have here is this type of a scenario, what is called as person by person optimality. This is not present. This, if was present, would have been called as team optimal. This is not the case. So now let's try and understand why that is. So if right. So another thing to notice is person by person optimality does not always mean that this is going to be the same as the global optimal or the team optimal. The optimal for both the controllers or all the multiple controllers. So now, to understand this second case better, let's take the case when both f and g are linear. Then what is the optimal cost under it? This is the work that is Witsenhausen's original work. So we are taking f and g both to be some things which are linear in their respective functions. Okay, there's a slight lag in what I'm saying and what is visible on the screen, so I'll go a bit slow. Is it stuck again? Okay, it's not responding. Okay, so what he did is he took the case where both of them were linear. In that scenario, the problem of finding the cost reduces to finding what is this um, gamma and mu, the optimal gamma and mu. If we take the initial state x to be a Gaussian with variance sigma square and v to be some Gaussian with variance just 1, then mu star, this mu, ends up having a form like this. This is, remember, for this all we are doing is we're just doing estimation. So that estimation ends up having mu of this kind. This is coming just from the properties of Gaussians. You could try it out yourself. It's fairly straightforward. So now that this mu star depends on the lambda, this j could be rewritten as something that depends on lambda and mu of lambda, meaning it's ultimately just a function of lambda only. So this is already done. Next step would be to optimize the whole thing. And to optimize the whole thing, and there's just one parameter, all you have to do is take the derivative and equate it to 0. It seems simple, but actually it's very complicated. And because of the whole complicatedness of the problem, Witsenhausen only talks about one particular region of the whole thing. So he says, in scenarios where k square is less than half, remember there was a k square u1 square term in the cost itself, so that particular k square. when this is the case, when k is less than 1/4, sorry, um, the minimization yields that the j star minimum is something 1 minus k square. And as you can notice, as k tends to 0, this would sorry tend to 1. So this is the kind of optimal cost he's able to get with linear controllers. And in the problem of using linear controllers, what he has done is he has tried to find out this particular scenario, but restricting himself to FL and GL both being linear. Now what he's showing is, this is a policy he constructed. It's not talked about as to how he constructed this policy. This is quite old, so people may have tried to understand the intuition behind it, but anyways, I'm not going to talk about any of that. So he's gonna just focus on this region. If in this region a policy can behave better than the linear optimal policy, or what is believed to be both linear and possibly optimal, if we can find something non-linear and better than this, the job is done. That serves as a counterexample. So for that, what he took was, he said, okay, let's take f of x to be some sort of a function like this. It's kind of a step function with some scaling done to it. And notice what this scaling means. This means when x equal to 0, or in our case we are rather talking about x zeros, right? When x0 is positive, some information is given, some binary information is encoded in f of x and given to the other controller, and that is what is used further on in the second part. So when he does this, he finds out that when he tries to work with this, he gets some j of this form. And here when he takes k to be tending to 0, he notices that the optimal that he can get is actually 0.5. Whereas in the previous situation, where we had taken the best linear we could get, best linear controllers we could get for f and g, that was 1. But here we have something non-linear which is better than that. So for this particular example at least, for the Witsenhausen scenario, this is definitely greater than the linear best and the linear best in G. But clearly there is something that may not be linear, so this is non-linear and still better. This suggests that we can no longer treat those two as separate problems. Fix one and then solve the other, fix one and solve the other, and plug them together. It doesn't always work, and that's not working here. Because if it were to work, this is where the problem would have stopped. But in reality, for this particular problem, we are able to show some policy which are both non-linear and they behave better than what we could have achieved with linear policies. So what this is showing is that even in LQG games, linear policies are not always optimal, and they are not optimal because there is dual effect, because there is non-classical information structure. So those are the two new things that came out of this. So now this is just the construction of the paper itself, and there's not much more to it. But notice what he came up with. So this f is a step function. This is some sigma, this is some minus sigma. Okay, this is f of x. On the other hand, g of x is the following. Remember, g would show up when we're actually doing g of f of x plus something. It depends on y. So typically, a tan hyperbolic has this type of a behavior. But since there is dependence of sigma inside also, so there's some scaling there. So the behavior might be slightly different, but the overall structure is still quite similar. Nevertheless, it's still highly non-linear. And this particular situation, this particular non-linear policy is telling us that action u1 has hidden some information about what kind of u uh, what kind of x0 it is, whether it's greater than 0 or not, or what. So even though we can't make complete inference as to what is the exact value of x0, but this is still some amount of inference. Maybe this inference is what helps in the next step with the estimation, and estimation becomes even better than what we could have achieved before.
And this is cytoscape signal.
This is
Signaling.
Yeah, this is what they refer to as signaling. This type of a behavior. Where indirectly u1 is trying to send information about the actual state to the next controller, because if it doesn't, we know what happens. It will behave like it has behaved in the previous case, which is it could do linear uh, policies, and linear policies are not the best ones that are out there. We can do better than that. So if it is possible to do better than that, the objective should be to try and put them together and optimize together, so they reach the true optimal or the global optimal, not just some local optima that they may have reached with only linear. Okay, so this is it from my side. Do you have any questions? Else I'll just take a quick recap of what we did today.
I have one example.
Yeah.
It's a real world example.
Yeah.
For example, like this shopkeeper who's selling shoes, and he knows the proper shoes and the material, everything. But I'm not aware because of packaging. The actual price he knows, but I don't know the actual price.
Okay. Buying price, selling price difference. Sure.
And his packaging is similar to noise. So
Okay.
I'm observing the shoes plus packaging and all this surrounding things. Maybe the placement or maybe the branding and all this. It's all the noise. Actual material is the shoes. Now, according to all these things, I can never be able to find a proper optimal with this information setting, right? If I don't know the actual shoes material by any signaling method or any shopkeeper behavior or past information, that is the crux of all this discussion.
That's the crux of it all. That if you don't know the complete information to make your decision will not be optimal in scenarios like this, scenarios where there is non-local, non-classical information, and there is dual effect that matters. There, something more will be needed. Your estimation needs to get better, and for your estimation to get better, so that's pretty much what is happening here. For your estimation to get better, u1 needs to somehow convey something more than it would convey from just linear policy.
Okay. Okay, like for example, this material is from this place, so that is this material is something like that.
Hmm.
But there should be some example right where both participated and have a solution. Maybe like CEO is conveying the information to the down people properly, and that signaling makes the whole team to be feeling optimal. I'm trying to make sense of the examples to have concrete and crux out of this discussion.
So, what kind of examples did we see for LQG games? We saw a few, right? Sorry, not games, LQG control problem. We saw a few scenarios where we actually used it. One was that one. One was the one with inventory control. What was it called? Um, but there it was complete information. So if instead of complete information, suppose you've placed an order for the next stock to arrive, but it has not arrived and you don't know when it will arrive. So with that uncertainty, maybe your observation is incomplete. Maybe it arrived, but you were not the one to take note of it, so you're not aware about it. So some uh, amount of noise in the observation. So if you're dealing with a system like that where there is, right, that's I think that's a very close example to what we're doing here. So the dynamics is linear. Let's say backlogging is allowed, so the dynamics stays that way, there's no max or anything. Then what we're dealing with is a quadratic cost. So the cost of keeping storage, the cost of um, ordering some new items, and some penalty if you've ordered more than needed, things of that kind. Now if you don't know what cost you would incur, sorry, if you don't know what is there in your inventory because something is in transit and you don't know when it will arrive, or if it has arrived in a given time frame where you did not check, for example, or there's some noise in your observation, then that will again affect the whole problem. So if we were to go just by the intuition from Witsenhausen that's coming out from all of this, then uh, what is U1 and U2? Okay, so in that sense, U1 is what order did you place for U1, U2 is what order did you place for U2. So if you just have the information of the order that you placed and that order telling you what was
Or YouTube will be the selling. How many have sold already?
no, that is the dynamics of the problem. That part is not the issue. How x1 x2 get updated, that is okay. U1 and U2 are your actions, as in the purchase orders you're placing. So if your
Okay.
purchase order, your U1, has some
Mhm.
information about x's that you could almost derive, maybe not completely infer, but still you're able to infer. If that is
Mhm.
available, then that could be used when you're making your next decision. Meaning, if you know what the action was, that's one thing, but we know knowing the action is not enough. So, apart from knowing the action, if the action itself tells you what must have been the state before. So if you're placing, so it's like saying if you place an order above 100, that means you're running very low in your stock inventory right now, and that's why you needed to place this much of an order. Or
Mhm.
if you keep a code, okay, if what I have in my stock is even number of things, then I'll order even number in my order. Otherwise, I'll order odd number. So that way, there might be an error in the cost that you'll incur because you're not ordering what you exactly need. You're ordering something above or below it. But this signaling, this referencing helps you in making your next decision. This tells you something about the previous one, the previous information, and that might help make a better decision at the next step, because what happens in the transit we don't know. What actually arrives may not be the complete quantity that you order. It may be a bit more or a bit less, and we don't know how more or less it will be. So
Okay.
yeah, so like it's in some sense saying it's a good idea to keep track of previous information in a encoded form, so that you can use it in your next decisions. You can't keep all the information because that's too much. Let's put it that way. You'll have um, limit in your memory space available, but you can keep some of it. So you can encode it in some way that could be useful next time. I think that's what Witsenhausen's problem. That could be the takeaway from Witsenhausen's problem if you apply it to LQG problems.
Okay.
I think this example gives you a little insight, but more than that, I think it needs to be thought out more carefully. But okay.
Because always in this problem example, I'm able to coming up only like two controller system. For example, this shopkeeper, this inventory control, and
Hmm.
a supplier. In between, I can make proper connection.
It's okay. Witzenhausen's whole thing is only for two controllers, and even then it's difficult to solve. It's because of the complexity of the problem, because it's highly nonlinear and all of that. So, even as an example, it may not be possible for you to extrapolate and think of an example where this could be useful, because you don't know if it will be or not. So, right away, it's okay to not be able to do that. I can try thinking about it next time, and we can discuss a few more examples related to this in similar scenarios, maybe LQG type scenarios, or I think next time onwards, decision problems might have some flavor of Witzenhausen. Flavor, not the exact thing. So, there we might get some easier examples to talk about all of these things.
One example, just to have a like Central Bank of India and then other banks.
Hmm.
So both have common goal to let's say inflation to under control. That is cost. But if the interest rate passed by the central bank will be the U1, and actual which the other banks are doing it, it's a U2. But this information sharing not able to do.
Hmm. Okay. I think it needs to be thought out more carefully. But you have to understand, here the controllers are not against each other in any way. They have a common thing that they're trying to optimize. They don't have different goals. It's not like one is
Okay.
trying to minimize, another is trying to maximize.
Mm-hmm.
If that is the scenario, that's competitive, that's non cooperative. That works very differently. This is, I feel, a simpler scenario because both are doing the same thing. They have the same goal. They want to optimize the exact same objective. Their role may be to only affect one part of it, but they're still interested in only minimizing a quantity.
But the noise is like as a central bank announced thing, the noise will be the market behavior, will be the
Sure.
noise to the bank,
Hmm.
like capital market and normal market both.
Hmm.
So actual thing is actual impact nobody knows. I don't know.
Yeah.
I need to think
Yeah, I
properly.
think looking for examples where Witzenhausen can be used in a practical sense, I think it needs to be thought out a little bit more carefully. I am actually not aware of um, what kind of areas where it is used. It's not my, everyday work. So I don't know about that. But I'll look it up and we can discuss this next time.
Yeah, sure.
Okay. So I'll just quickly recap what we did today. So we started talking about the Witsenhausen's problem. We compared the scenario here to what we have seen in MDPs or other Markov policy type problems, and we noticed that dependence between current action and the previous action, or current policy and previous policy, that kind of dependence is typically there. In MDP type problems with Markov policy, that dependence doesn't matter to manifest at the level of cost. On the other hand, with non-classical problems, it matters because it affects the cost in a non-linear fashion. There are dependence of one function on the other. One policy depends on the policy of the other. Then we talked about what we mean by this dual effect, meaning how the information of one, or rather the policy of controller 1 affects the information of controller 2. That's what is referred to as the dual effect. Apart from obviously affecting the cost. Cost is affected by actions, that's by default. So we looked at a few variants of Witsenhausen's problem, as in whether there is dual effect or not. That's the point that we were trying to understand. So we saw two scenarios where there was no dual effect. It was having full noise, meaning we had x0 and the noise itself, or having both the observations y0 and y1. These two were anyways equivalent, and both of these scenarios were such that there was no dual effect. Next, we saw two variants where there was a dual effect. So in this scenario, instead of using some information, some x0, x1 or something, it's the action of the previous controller that is known, y1 and the action. This does not reduce to the same form as we saw in the previous variants, and because of that there is a dual effect. And we showed that there is a dual effect by taking two different policies, gamma 1. Using that, we showed what is the effect on the knowledge that is being used by gamma 2 or the controller 2, and we saw that that's not the same in general. Also, we showed that in such a scenario, in such a variant, uh, it will not be possible to get an optimal solution, for the simple reason that gamma 2 needs to make an estimation about the state x0 when it only knows x0 plus some noise. So a complete estimation is not possible in general, and hence this term will cause problem, and without having this term there'll be some error and the optimal value will not go to 0. Then we talked about the fourth case where we saw a standard MDP type problem with complete information, or that the policies are chosen in a Markovian fashion. In that case, we saw that still there is a dual effect, meaning the choice of gamma 1 does affect the information of the other controller. Here there is dependence on x0, there is no dependence on x0, so the effect is there. But even though there is this dual effect, it does not matter much when we are solving for the optimal value. Reason being, here u2 just needs to use x1 and minimize this, so it can just use the value x1 itself. It's not making any estimations here, so it can find the optimal. And finally, we talked about the Witsenhausen's problem. To talk about this problem, first we started by saying that suppose we take the case where f is linear and find the best response of g. We found out the best response is linear. The other way around, if we take g to be linear, we find that the best response of f in that case is linear. But this is actually person by person optimality. This is not the same as having team optimality or global optimality. To get global optimality, we will have to optimize both of them together. If by default we assume that okay, let's go by linear best linear strategies that we can find, or best linear policies that we can find, then in a particular region where k is a certain amount of value, so if k square is less than 1/4, then this is what it comes out to be. On the other hand, if instead of restricting ourselves to linear policies, if this f and g were allowed to be non-linear, or something where there is some kind of signaling, then the j can be less than half when k tends to 0. On the other hand, in the previous case, when we were talking about just linearly best strategies, there j could go all the way till, could only be 1, it could only tend to 1, meaning this is better. So non-linear strategies could get better value, better j value, better cost, minimize the cost better. And this is happening because we are in the region with non-classical information and there is dual effect. And this becomes a counterexample to the fact that LQG typically has linear policies. This is the scenario where LQG does not have linear policies. So the take home message is LQG with classical information structure will still have linear policies, but not when there is non-classical information structure and dual effect. And this was Witsenhausen's counterexample. Alright, so if there are no more questions, we can pause here.
Thank you.
Okay, thank you, bye bye.